Right, well, I think that's given everyone time to get over from the opening comments. So first of all, I'm James Goodman. I'm co-chair of this session, the 11th AI and Games Symposium, along with Cristiano Pacheco, who is co-chairing with me, not least so that we can each introduce each other when we're talking, otherwise it might get embarrassing. So welcome to the 11th Symposium. Obviously, this is a combination of 2 years, so we're all here a year later than first anticipated, and in many cases, with perhaps rather more hair than we would like. We have quite a brief agenda today. We've got a total of 5 talks, so we'll be finishing a little earlier, and it does mean that we've been able to put 2 talks into each slot, which means that there shouldn't be any need for the speakers to hurry up too much, and there will be plenty of time for questions. So this afternoon, we've got the first 2 talks, one from Martin Baller at Queen Mary on using map elites, and then after that, Nathan John-McDougall, also from Queen Mary, who I think we have a video from him. It's more of a demonstration paper, so he's trying to work out how he can do that over video. So I think if we're all ready, Martin, I'll hand over to you for your map elites talk.
Okay, thank you. So I'm trying to share my screen quickly. Oh, might be the wrong screen. Do you see the slides?
I can see, yes, a slide in PowerPoint or in Google Docs, in Google presentation.
Okay, and is it full screen now?
It's now full screen, yes.
Oh, okay, fine. So
one thing I forgot to mention, obviously, given it's virtual, what I'll do is I will chat in the Zoom chat at 5 minutes and 1 minute rather than trying to hold up a piece of paper for you.
Okay, I'm not sure if I can see the chat at the meantime. It only shows me my slides full screen.
Fine. In that case, I'll just shout at you when you run out of time.
Okay, that's fine. Okay, so then I get started. So this is a collaboration between multiple people, including Adrian, Adam, Nuria, and Ryan, and me, Martin Balla. And a quick outline of this talk. I'm going to start by explaining the problem we are working with, which is game parameter search. Then I'm going to talk about objective-based search, and then the map elites algorithm. Then I'm going to show you the game that we use for our experiment, which is called Caves.
Right, so just to confirm everyone's seen James's comment in the chat that Sven would like us to join the main session after the break, given that we had a slight change of plan with breakouts. Okay, Martin, do you want to start again?
Okay, so from the beginning, or where did I crash?
Just start from the beginning, it's probably easier.
Okay, yeah. Maybe from here. Okay, so my name is Martin Balla, and I present you this work, which is a collaboration between Adrian, Adam, Nuria, Ryan, and me, between the Queen Mary University of London and University of York. So just a quick outline of the talk. I'm going to start by introducing the problem, which is game parameter search. Then I'm going to talk about objective-based search, then more specifically about the map elites algorithm. Then I show you the game that we used in our experiments, which is called Cave Swing. Then I show some results and a conclusion at the end. So the game parameters are something that we come across in games very often when we design them. So these are mainly all the variables in the game. So for example, in a first-person shooter game, it can be the health or the damage a gun does or the accuracy of the gun. But you can also see them in classical board game, like in Settlers of Catan, a variable could be the cost of a road or the cost of a settlement. But you can also see parameters in level generators. So for example, for Mario, there are generators which requires some parameters as argument, for example, the number of enemies you want on the level, or the number of platforms, etc. And we just think all of these as parameters. We set this search space of all the possible parameters in a game, and we are interested in finding interesting solutions. To do that, we can use an objective-based optimization algorithm, which requires a fitness function, which is not obvious how to define it. So for example, if you define your fitness function as the game score, you might get the easiest level that you can think of. And when you run the optimization algorithm, you might
exploration across all the tuples that match. So it's exactly the same as we do when we try to predict the average score. So just as a recap, with NTBR, first of all, we generate k different values of theta, which we use a random evolution strategy that simply randomly mutates the individual settings from the previously tried one. For each of those, we use the n-tuple model to predict what the value is going to be, and then we add on a second amount to encourage exploration of tuples or settings theta, which we haven't tried much before. And this simple averaging is really rather dodgy in my view. It suggests that all tuples are equal, which is really very unlikely, especially as we get more data. And perhaps an example illustrates that. If we consider the situation with the previous example, where we've now run 1,000 different trials of the game. As you can see, 431 of those trials have had medium speed, and that's had a very high success rate of 81% out of those. But yeah, 89 of them were in the jungle, and in which only 2 of them won. But we can actually then see, in this case, we have the 2 tuples and the 3 tuple as well. So we can also then see that if you're medium speed in the jungle, well, you still do pretty badly, but the average is perhaps slightly better than if you just knew you're in the jungle. But you can see there's a lot of interaction between those. But there is I think a very valid question is, well, why should we use the very high score for the medium speed when we know we're in the jungle and we know that's going to dramatically reduce our score? But what NTBR does is a very crude and simple average. It takes all 7 of those numbers and takes the average and gets a prediction of 0.202 in this particular case. And the expectation really, and this is what drove this initial idea, was that medium result, for example, is a huge overestimate as it includes all the non-jungle data. And that maybe what we should be doing is using, when we have more data, ignoring the 1 tuples in favor of the 2 tuples and the 3 tuples, which take account of the interactions between the parameters. And this is what we try to do with this then, is we picked, the idea here is, if we have a lot of data at the 3 tuple or indeed at the 2 tuple, then that should shield the lower tuples below it, because those are much more general and we've got good enough information now that we should be able to ignore them. And we used 4 different weighting functions shown on the right, a linear, exponential, inverse, and inverse square root, which, as you can see, decay at increasing rates. And then what the adaptation to the algorithm was simply to say that when we take the value, we weight the top level tuple, the TP, the top tuple, by omega, which goes up to 1 at the top of the graph, and then any weighting left over, then we use all of the recursive tuples below that and add those in. So when we have no data on the top tuple, we only use the lower tuples, but as we get more and more data on the top tuple, the lower tuples should be increasingly degraded in their contribution to the final prediction. We then wanted to try this on 4 functions. The idea here was that games are great, but they can be quite expensive to run. And since what we're trying to do here was to test did this change the algorithm, improve its ability to find an optimal position, we really wanted to start with some complex functions that we knew what the optimal position was, and above all, they were going to be easy and cheap to evaluate. So we took 4 examples from the operational research literature. The two-dimensional ones are shown in those graphs as the Brannin and the Goldstein price. Those are quite simple. The 2 Hartman ones, which are 3-dimensional and 6-dimensional respectively, they're designed to have 2 or 4 optimal wide distances in the space, one of which is slightly better than the others. And in the classic operational research literature, you'd be interested in, can we find a single global optimum? Whereas here, honestly, we're usually more concerned about just finding a very good answer. And the other crucial change is that, yes, games are stochastic. You use a set of parameters and it gives you a chance of winning. It doesn't definitively give you a win or a lose. And that's one of the things that makes the optimization much more challenging, is that noise level. So to emulate that, we use the underlying function to convert to a probability between 0 and 1, and then we use that to roll a random number, and then based on that is the result we actually returned from the black box. So that gives us some fast evaluation that we can now measure to see, do these algorithmic changes actually improve its ability to find the optimal setting? However, we did think we should probably do some games as well. So we used the classic games of Asteroids and a slightly less classic game of Planet Wars. And what we did here, in an echo of Martin's work earlier, is to use Rolling Horizon in the evolutionary algorithm. The precise parameters shown here aren't terribly important. They're just different ways you can parameterize the algorithm. The first 2 columns have a very small total parameter space that we're trying to explore, 200 or 300. Those were from the original paper by Simon Lucas that started looking at this algorithm. And then what we added in was the latter 2, which had significantly more settings, both new parameter dimensions and also new settings within each of those dimensions. And the idea here is that these are very much, with 23,000, there's no feasible way you're ever going to be able to exhaustively search that space. So therefore, it's particularly interesting if can the algorithm give us a good approximate answer to a good setting, even though it can only explore a tiny fraction of the space. What we then did was, for the functions, we ran each of the 5 NTVIA variants. So that's the classic NTVIA, which just does the very crude average, and then the 4 variants that we considered, each with a different weighting function, for 300, 1,000, and 3,000 trials, and we did that 1,000 times. So by repeating it 1,000 times, we can get a distribution of how frequently any individual NTVIA run gives us the best or near optimal value. Then for the games, for the smaller game sizes, we just ran a number of trials equal to the parameter settings. And again, we could repeat that sufficiently many times to get an idea of how frequently did we find a good setting. And one of the things that led on to is that sometimes NTVIA would, as an optimizer, it would be quite a poor optimizer, and sometimes it would give you a pretty duff answer. So the question then arose, well, given, as is usually the case, we have a finite budget of, we want to optimize these parameters, and we've got 10,000 games, or say 20,000 games we can run. What's the best way to do it? Is it to put all of those 20,000 trials into a single optimization run, or should we split them up and do 10 independent trials of 2,000 each and just take the best? So we look at the results. The first one, I've got just showing a couple here. The first one, this is the 3-dimensional Hartman function. So these are just notch box plots that show the range of values over all 1,000 runs. And you can see they all do pretty well. They all, at least some of the runs, find the best value. But what you can see is that if you look at the dark blue are the standard ones, and then the others are the different variants. And I apologize, the key is actually slightly wrong. It's actually all the 300 iterations are on the left, all the 1,000 iterations in the middle, and all the 3,000 on the right-hand side. And if you just look, for example, at the left-handmost 5 box plots, you can see they're all pretty much the same, and that there's really no significant difference between them, and that you may as well use the standard NTVIA because it's just as good as the others. And that was actually reflected across all of them. It's even more clear in this case. So this is now a much harder problem. It's 6 dimensions. And you can see in the first 5 columns that actually by far the best is the vanilla NTBA algorithm. And all of this fancy, you know, fanning about with weighting functions in a recursive way, actually what it does is it harms performance. And that applies just as much to the 1000 and the 3000. In each case, the dark blue is the best.
You have about 2 minutes.
The games, we found exactly the same thing. The only thing I wanted to highlight is the one thing NTBA was bad at, which the other variants were good at, was predicting the actual value. So the bottom plot here, the red line at 0 shows a perfect prediction of the score. And NTBA was often quite poor at that, but it doesn't really matter because we're not trying to get a perfect prediction from NTBA, we're just trying to get out what is a good parameter setting. And then the final question, which was how do we spend a fixed budget of game computations? And the answer here was very, very clear, which was don't spend it all on one budget. What you actually want to do is to split that up. And if you've got 20,000 games, run 20 separate optimization runs completely independent of each other, because each of them will end up with, given the high stochasticity, pick a different value. And then what you can do is just test those 20 values to find out which of those is the best. And in every single case, that gave, you know, a better result than putting all of your computational budget into a single basket. Many baskets was much better. So this was really, although the initial attempt to find a better way of modifying the optimization algorithm failed rather dismally, it did at least have this slight silver lining that it has now confirmed the best way to use the algorithm to get a reliable result rather than just relying on a single optimization run. So final thanks to Simon Lucas for helping with the work, and particularly David Zendel for inspiring it in the first place with some comments he made. Any questions from anyone?
No, I can't see everyone, but I'm not seeing any questions. At least I do have one, which is, since you kind of noticed that this didn't particularly work as well you were hoping for, so what would be your next steps then? Like what exactly do you think you would do next from here?
Well, I did try. I've tried a couple of other things, and they failed equally as much, which was again using rather more sophisticated regression techniques to try and work out which tuples were crucial to predicting success and which other parameter settings were a bit irrelevant. So I think what I've now concluded is I should give up on that, and just it's one of those remarkable situations that it's crude, it's simple, it just seems to work exceptionally well, and why look a gift horse in the mouth?
Fair enough, okay. Anyone else has any questions? Anything to add? Okay, that's him.
Right, in that case, shall I take over as chair? And the next talk we have is from Cristiano Pacheco, and that's it. It's about co-evolutionary rolling horizon adversarial algorithms. Yes. So let me know, Christiana, if you're ready to go.
I believe so, yeah. I was just gonna get to share my screen, because I think if I do this, you should be seeing my presentation.
Yep, right? It's not yet in present mode, but
yes, this should be now in present mode.
That's perfect.
Okay, well, that's
over to you.
Right. So as mentioned, I will be talking about a little bit of a change we did as a group to the default Raya algorithm that's in GBGI. So this was a work we did quite a long time ago between me, Christina, Charlie, and Diego being my supervisor. And so essentially, as for an overview of what this is that I'm gonna talk a little bit about what GBGI is for those who may not know. I think it's fairly known, but just in case. Also the algorithms that were kind of that were in this process, and the experimentation, what we kind of got out of it, and what we intend to do for what would be a possibility of the future work. So there are many competitions. They kind of used to test AI, so this is not news. From Super Mario to StarCraft, there's been many. Some frameworks were more developed to tackle general gameplay. So, AI that can be applied in several settings and not just a very specific game. OpenAI did this with their OpenAI Gym, arcade learning environment, and so on. However, we focused on using the general video game AI, so now known for GVG AI, because it offered a few things. So for starters, it did offer forward model. Some frameworks do not do this. Also brings some agents that already be created, has over 80 public available games. There are a few more when you do the competitions, and it's mostly based on arcade puzzle-like games for simplicity, and it has both single tracks and multiplayer tracks. So in our case, the thing we focused the most on was actually on the two-player track. Our main focus was here because it has some differences. Once again, we wanted to use the opponent, and you can only do it if you have two players. There are some differences, as I said, some actions. So in this case, the actions are applied to all agents. It helps on guessing opponent, and it introduces both cooperative and competitive games. So also means that you end up having more interactions, you end up having different score systems and end conditions. And so this is why we kind of went with this one. So this is more of an example of what a game would typically look like. So this is the GVGI version of Sokoban. And you can see, for example, in this game, you have those two spots where you have to put the boxes, and clearly one gets stuck if the other agent doesn't cooperate and takes the box from where the other one left off. And so they can both drag the boxes in a cooperative manner to win this game. So there are obviously a few very, or let's say the most popular algorithms used in GVGI so far. One of them is Monte Carlo tree search, and the other one being Rolling Horizon evolutionary algorithms, which I'm going to call it Raya from here onwards for simplicity. Raya is more the thing we focused on, so that's why that is highlighted. I'm not going to go into massive detail into these algorithms, mostly because people already know them, and also because it's a shorter presentation. But overall, Monte Carlo tree search performs pretty much 4 steps. It selects a node out of a tree, it expands the children, simulates this with random movements, and then it just backpropagates this information to update the parent in the tree. And this is repeated until the predefined computational budget has been reached. As for Raya, in this case, using the statistical forward planning algorithms, so there's each individual has genes, and so these represent the action plans that they have for the game. And initially, it tends to form a random one, so of sequential actions. The evaluation tends to be done by stepping through each action. You apply it and use a heuristic to understand or to know what's the fitness of those actions. A new population gets evolved by using genetic operators. Genetic operators. So you can pick the best one. You can cross them over. You can just randomly mutate them. There's different ways of going about this. And once again, this is done until the computational budget gets hit. So why Rolling Horizon coevolutionary planning? So our motivation here was, well, it would make sense that we think about what our opponents are actually doing in the games. If we have a decent idea of what the other person is doing, we can counter them a lot better. So ideally, you have more of a fighting chance if you know, or if you somewhat guess what your opponent is trying to do. So if we assume that our opponent is rational and that Ray is a reasonable algorithm, then why not try to model for that opponent? So the concept then was to develop a plan for the agent and the best guess plan for the opponent. So this is a difference between Ray, because Ray would do just its own plan, and in this case, it tries to do both. And you can use that plan to evaluate this plan, so the player plans and the opponent's plan, and vice versa. Implementation, as mentioned, is based off of the actual default Raya agent that GBGI brings with. And each iteration, or the difference is that in each iteration, we evolve a player plan and an opponent plan, which means some of that budget that we have available has now to be given to evolve the opponent's plan as long as same as the player one. So a bit on more pseudocode side, what it basically does there, what initializes the player plan and the opponent plan, it either gives a shift buffer or a random sequence if it's the first move. And while there is a budget, it evaluates the plan, the player plans, taking the opponents, taking into regard the opponents, it evolves it. Same thing then for the opponent, but with the player. What it returns is essentially the first move of the best player plan that it could come up with. What we do for the evolutionary strategy is using the Mu and Lambda strategy. So what this basically means, Mu is the number of picks for the most fit individuals. In this case, we use 1, and it's through etalism. So it's the best one that there is. It's the one you pick. And the lambda being the number of individuals that you are producing from that population. In this case, we produce 4. The population size that you start with is 5, and what we have as a sequence list is 20. And we do use a shift buffer here. And also we do apply some random mutation. As for the opponent plan, we actually went with a simpler one because it does use less computation. So we went with what's called the IMHC. And what it essentially does is that it's another type of evolutionary algorithm where there's a population of 1. And what it does is that it assesses its fitness and it mutates it, then assesses that mutation. If the mutation is better, you substitute that with that one. If it isn't, then you keep doing this until you reach the limit of for how long you can be doing this. Population size of this we are using, as I said, 1. Sequence was the same, also the same genetic operators. We just did not have the shift buffer here on this one. So the experiment essentially ended up being using different games, 10 games from the double player on the GBGAI. So as it is a quite variety of games, it has cooperative or competitive, it has both symmetric and asymmetric, same thing with stochastic or deterministic. And again, you get on the slide, you can see the differences of the games. I did leave on the paper, the paper has an explanation of each game because with asteroids, everyone knows what it is, but the others are usually just adaptations of quite well-known puzzle and arcade games. We tested 4 algorithms to kind of compare what they do. The one we created, obviously, Raya, since it's supposed to be a little extra on it, so we want to see how it fares against it. MCTS, since it's the other one that's mostly used, and random because it's always nice to have a baseline random there. So it essentially there's 10 games, each has about 5 levels. You let them play on 2 sides, so you get 100 trials per training. And so you get in total about 1,000 matches that this all goes through. And what we got in the results was essentially so we did all games played across all 6 pairings of agents, so we could have everyone facing everyone. And for each pair, there wins against each other per game. So if you see, for example, a RHCP versus Raya, the total it says 360, 309 means that RHCP won 360 games, Raya won 3,009. And you have the different games from 0 to 9 on the left side. So on the actual Raya, which is essentially what we try to improve on, it did operate fairly similar, despite the cost, because it does have a cost in the computational time. But overall, it actually won a bit more in the games than Raya did. So that's a fairly positive outcome. However, when you compare RHCP and Raya, so both of them against MCTS still remains the dominant algorithm, winning over both. So despite that we did improve a little bit, it is still not beating MCTS. It does seem to compete a bit more, but it's not really a match still for it. If you look at the numbers of 154 versus, 530 and so on. As for random, well, understandably, they all performed better than random. They are making some decisions after all, so that's not too bad. And then we also check the accuracy of our algorithm, so RHCP. And what we found is that it actually has fairly low accuracies. The highest ones are basically in bold here, and you can see that they even well below 50%. So it's actually not guessing very well what the other agent is doing, which is not very helpful. So essentially, RCP is performing better than Raya. It provides a small improvement, not a massive one. And MCTS does remain as the winning algorithm. Now, Raya, as mentioned in 2 talks already, or rolling horizon agents and any sort of evolutionary algorithms, they are very hyperparameter sensitive. So results could possibly improve if you use a wider range of parameters. And also predictions were very low, which is not going to help it towards beating the algorithm. So it's not really doing a good job at even guessing more or less how the other agents are doing. Now, a possible reason for this might be the stochastic nature of said evolutionary algorithms, coupled with a small number of the evolution iterations, because they don't do that many. So that can always be a little bit problematic. So essentially, the conclusion we took from this was that thinking about your opponent is fantastic, and in theory is also an amazing idea. However, in our case, it only showed a very small improvement and not even beating overall. So it's still below what was the top positions. Now, yes, this can be because the evaluations are initially based on a bad opponent plan, and maybe if it was better, it would do better. We also are wasting resources on the opponent's plan, and it might very well be overthinking what a random agent is doing. So although solutions where results might lie in hyperparameter tuning, it's still, an increase of resources or smaller rollouts, it's still not guaranteed that you're going to have a fantastic result out of this, if not just a small improvement. That's it. And as for my contact details, that's my email. I also have Twitter, which I would very much not recommend reaching me out on because I never use it. But there is LinkedIn and my actual email. Those are a lot safer bets if you do want to reach out to me. Any questions?
I've got one quick one.
Okay.
First of all, just from the table of the results, were there any games that you found that the co-evolutionary approach did work better on, or was it always outclassed by Monte Carlo tree search?
Let me stop. Oh dear. Ooh, okay. Let me check, because on this table we kind of just put the names as is, so it's not overly helpful. But there were some games or others that it did slightly better. I was trying to remember which one was it. Because even against MCTS, there was some games it was able to compete a little bit more. Like for example, game number 4. What that essentially is gotcha. So it's the player has to chase the other one.
But actually, game number 4 is 50-50 in every single setting. So actually. So
yeah. So but then you have that which in gotcha it's it does 50-50 on all of them. So it's not a massive improvement.
It's a gamble rather than the game.
It is. I mean, after all, the game is just literally go next to the other one. So just grab it. And even randomly, that might not be incredibly hard to do. But on the other one, where it competed a bit more, was 6, which is also very averaged out on all of them. And that's clacks. So it has just colored objects falling from the sky. And the players catch them for points. So if you catch your own color, you gain points. If you catch the other color, you don't. I think you end up actually losing points. And the person that wins, or the agent that wins, is the one that catches the most. So, but as seen, when it does slightly okay against it, it kind of does, everyone does slightly okay on those. So it's not an ideal result, no.
Okay, no, so I'm also just thinking, the second observation I think was, I would suspect that part of the reason it might be doing better is because it doesn't need to predict what the opponent's actually going to do, as long as it's good at predicting the worst thing they could do and does something to stop that causing a problem.
Yeah.
And I can see that there could be a sort of a risk aversion of the co-evolution approach could be quite helpful in avoiding complete gotcha traps that RIA might be vulnerable to.
Yeah, I mean, as I said, it's quite stochastic how it kind of comes up with its own solutions, and it might be that it's just trying to counter in the worst and not the best possible. And again, these are fairly simple games as well, and nothing is really being given rules wise. So in the end, it's kind of very random how they come up with things and go about doing things. And yes, in a sense, you're also spending budget, as I mentioned, on checking for the opponent's plan, which might not even be necessary here. So it might be a waste of resources in the end that it's not necessary to use.
Great. Any other questions from anyone in the audience? In which case, we are now perfectly back on time at 10 to 3. So we now pause for a break and then come back at 3 o'clock for Chris Madge on Word Clicker.
Yep. I think it's probably all right to start now. So I'm gonna give now the microphone to Chris so he can go and talk about the demo he's been developing. So Chris, off to you.
Thank you. Was that shared okay? Yeah. So yeah, my name is Chris Madge and I work as part of the DALI team at the Queen Mary University of London. And the DALI team is looking at natural language processing, supervised machine learning, but also how to gather the corpora for training supervised machine learning systems. And one of the approaches that we take to do that is using games with a purpose. So this is leading on from some work I've done in the past in making one of these games. So the problem that we set out to solve was how could we use games to gather natural language resources in the form of annotations. So these annotations are often quite complex, and the process of annotating doesn't, if I don't know if anyone's ever used like a text annotation interface, but they don't look very game-like. So that's it creates quite a challenging design space. So we've sort of split this problem into two phases. And the first thing we looked at, and this is previous work, is how can we get the mechanic of text annotation into a game that people want to play. And then the second one, which this work looks at, is how can we actually use that game to gather annotations. So these are kind of quite different problems in a way. For the second one, the kind of challenges that we're facing is how do we deal with things like uncertainty, right? We don't know what type of, when the player is right or wrong, for example. In a game, you normally reward players immediately for taking the correct action. So we created the game Word Clicker, which is up online, wordclicker.com, which people can play right now. And this was some work that was published at KaiPlay. So we had these challenges of, if we're going to create this game with a purpose, we need to overcome problems such as, for example, it can't cost a great deal of money. It has to be really inexpensive, because if it costs a lot of money to create as many types of games do, then it'll probably be cheaper to get all our annotations from another method, like, for example, crowdsourcing with Amazon Mechanical Turk, which is another idea we've explored in the past. It also needs to be repetitive. It's a repetitive thing, annotation. So we need a game that supports that, and it needs to be infinite as well in its play. If we have to architect a storyline in line with the amount of annotations that we need, then we'd effectively end up doing more work than the annotation effort itself. We need game design that provides a high ludic efficiency, right? I mean, a lot of games out there are games because they seek to deliberately problematize their interfaces. For example, things like Mortal Kombat, where you have to press the correct sequence of buttons on your keypad to do a kick. We can't have it so that the player not being able to press the correct sequence of buttons means that they make the wrong annotation. We want them to have an optimal route through making annotations that's efficient as possible and gets as many annotations as we can. And we also need the game to be kind of casual and inclusive of a lot of different player types. Okay, so a lot of people that annotate might not necessarily be game players, and we don't want to alienate that audience. We want a broader audience, as broad as audience as we possibly can get, to join the annotation effort. So this is the game design that we this is the original version of Word Clicker. So it starts off with this interactive tutorial which walks the players through the step. But basically what you're looking at is a typical clicker game. So in a clicker game, you have this core game loop where you start interacting with the game, and you're pretty much most of your time is spent just clicking, right? That's the kind of efficiency that we were looking for. So you click on something, you get a reward for clicking. Using those rewards, you make a purchase, which accelerates the gameplay. In effect, so you have to do less clicking or less work, or things get more generally exciting in the game. So we replaced that clicking, just clicking, with clicking annotations. So in Word Clicker, a player makes an annotation. In this case, they select the lexical category of a specific part of speech. So that could be a noun, an adjective, or a verb, or as the game progresses, there's different categories that come in. And by doing that, they collect ingredients in this ingredients jars at the top. These then go on to make different cakes, and that builds the virtual currency in the game of the money, and they can use that money to buy upgrades. So this just kind of progresses through and through. We can continue to present the player with different texts, and this worked out really quite well. So a lot of these game of purposes designs that have been proposed suffer from quite poor retention, quite short play times. So someone can come along, they're trying to provide you with text, and after, in some cases, like a minute or two, they're gone from the game, and that doesn't really work. What you want is a player that stays for a long time, slowly gets better and better with their knowledge, and makes an increasing contribution. And we kind of seem to achieve this with this game design. It fits quite well. It gave us, I think, an average of a 25-minute playtime. You can see the full details of this in that original work. That's just to give some background. What we needed to do next is actually take this to a place where, beyond having the text annotation mechanic in the game, we were actually gathering annotations. The first thing we needed to do and worry about was that we were actually giving the players good feedback about the annotations that they were providing. Right, that now started to matter. Whether or not they were right or wrong, beyond being entertaining for them, we needed to let them know how they were doing, how they were progressing through the game, and about their contribution. But we didn't want to kind of break the immersion. Right, we didn't want to start having discussions with the player about things like accuracy or F1 scores or things like that, because that just wouldn't be the same anymore. That wouldn't be very game-like. So instead, what we did is we allowed the player to view their how they were doing in the game as the sorry, excuse me. Allowed the player to see what they were doing in the game with a company report that dropped down, and this kind of told them about their accuracy in the game, and it was disguised as their reputation of their bakery to fit in with the kind of narrative of the game. The next thing we wanted to do was to increase the precision. So in games, players sort of adopt this behavior where they, there's you have an infinite number of lives, and you just carry on, you explore, and you do whatever you want. We wanted to softly encourage the player to make consistently correct judgments. So the judgments that we end up feeding into our NLP pipelines are accurate. But this is a bit tricky because it kind of goes against the design of the clicker games, which have they're incremental games. They're always ramping up and giving the player more and more rewards. So what we're doing here is use a streak mechanic. And what the streak mechanic does is, each time they correctly mark something, they get another cake beneath the large cake on the left-hand side, and 5 consistent judgments means that the game pushes into this sugar rush, at which point they're awarded with double points. So we're never penalizing the user exactly, we just give them more for being more consistent. As you can see, this kind of animation that happens now, and they get double the amount of points. So that was our way of approaching the precision challenge. The next thing I wanted to look at is how to tackle increasing recall. When we were looking through the numbers, some players preferred to get one part of speech, and since they were just kind of chasing getting the most money and the most cakes, they would just label that one part of speech, right? They would know what a noun is, they'd have a good notion of what a noun meant. They might not be so familiar with another part of speech tag, and they'd avoid those and just mark the nouns. So to achieve this, instead we required that the player have ingredients present in all the jars. That's to say that they would label the broad spectrum of all the parts of speech they had available to them at any one time before they would start to amass rewards. So as you can see here, no rewards are being given, unlike the original word clicker, until such, and it's asking them to find the remaining part of speech tag. And when they do so, they finally start accumulating rewards and the game starts. So that's how we got precision and recall. So the final challenge was dealing with annotations that where we didn't know what the answer was from before. So the way we tackled this was to insert these mystery rounds into the game, where when we were acquiring new annotations, we would just let the player know that we didn't know. Basically, at that time, we weren't going to tell them whether they got it right or not. We'd flash some question marks up in the background, and we'd tell them they could go ahead and label, and they would be given their rewards sort of retrospectively. So when we found out through a process of aggregating their annotations with other player annotations, whether or not they were right or wrong, at that point in the future, they would be given a reward. So it's quite kind of, there's a delicate interplay between all these different mechanics, right? When you launch these mechanics into a game, it's difficult to know exactly what the impact's going to be, because there's two goals that don't always run parallel here. On one side, you want to gather accurate annotations. On the other side, you've got to entertain a player. So doing something like, for example, trying to ramp up your precision in terms of your annotation, but could have a negative impact on the enjoyability of the game and result in players leaving. And with the different aggregation methods we have, for example, it could be that you might decide, okay, well, I'm prepared to take a bit of a hit on precision, or prepared to take a hit on recall, because if I can get a large enough number of players, then I can still find the answers with a high degree of accuracy. So these are the things all kind of need to be tuned and balanced, and that's something that we haven't done yet, is to examine the impact of these mechanics. Yeah, so you can play the new prototype version of WordClicker over at dev.wordclicker.com. The original version is still on wordclicker.com. And yeah, any questions?
Well, I do have one.
Yeah.
I'm curious, how did you outsource this essentially? How did you get participants for this? Like, is there any place where you're actively trying to get people to notice this? Are you sharing through university emails? Yeah.
So over time, depending on the experiment, I mean, for this particular experiment and the experiment for the original version of WordClicker, it's launched on indie game websites. And the reason for that choice is that we wanted to create a test environment with the kind of the most testing test environment, right? That we were working with people who are game players and weren't necessarily linguists. They didn't have any prior interests specifically in linguistics or annotation. We wanted to see if we could attract gamers, because that's I think the kind of true goal of these things is attracting a really broad range of people. Depending on the kind of the nature of experiment, in the past we've done a lot of stuff with Amazon Mechanical Turk. So, but it depends on the research question. For this particular one, it's indie game websites where you can go on, things like Newgrounds and Congregate, those sort of websites. You can go on and deploy your game, and as people looking to play indie games. But yeah, in the past it's been when we've needed to test a mechanic or an idea with thousands of people in terms of like a rapid prototype in exercise, then it's been with Amazon Mechanical Turk.
Also, since I noticed you called it the word clicker. Are you taking ideas out of the cookie clicker?
Exactly.
One?
Yeah. That's part of the inspiration for. I mean, that was one of the original clicker games, right? And that was a big part of the inspiration for this game. I mean, it just so turns out that those games and the design around there is it looks basic, but it's actually quite a clever kind of. It's got a lot of behavioral economics and psychology and things, I think, that go into those ideas to provide that kind of experience. And that seems to fit really well with the kind of thing that we're trying to do, in terms of our design constraints.
Okay. Does anyone else have any questions? Because if not, I will pass it on. Okay, well, James does. Go on.
Just one. I'm just very curious in terms of when you've got hold of indie gamers, how accurate are they as natural language process annotators?
So yeah, it depends on the exercise. For parts of speech, this is not too challenging, right? In the past, when I've done things like labeling noun phrases, for example, that can be a bit more. That gave some not so great results, but I like to think that there's a way that we can like architect the games. Provide a fantastic opportunity for learning, right? So we can sort of design the learning thing into the game, and that has to be fine-tuned and got right. And so I've had accuracies well over 80% with non-expert annotators, subject to taking, doing aggregation. So it can be really quite good, but it nearly always requires some fine tuning.
Because I just wonder as well whether, because I'm looking at whether primary schools might be a good target, given that, I know from personal experience that there's an awful lot of noun phrase identification, for example, on the current primary school curriculum. And that might be an awful lot more engaging than some other didactic techniques.
I think there's one of the goals we've looked at is trying to do both things at the same time. Which is sort of, I think, what Duolingo did for a while, right? You can learn a foreign language while you're contributing towards them collecting annotations about foreign language. Yeah, it's not something we've looked at a couple of times in the past. It's not something we've really fully explored. I think that would be really cool. Yeah, absolutely.
Any more questions? Always have to go up and down on the sidebars to see if anyone is raising their hands, so that's why. Okay, well, if no one has any more questions, I do think we have arrived at the end of our sessions. So James, do you want to take it from there?
No, I think thank you very much for turning up. As I said, we didn't have quite a full day, but thank you to all our speakers, and thank you to everyone for coping with the technical difficulties at the start of the morning. I think we got through those quite safely. So hopefully see people back maybe in a year's time, hopefully in the flesh.
Hopefully.